method. So maybe many of you are not familiar with this subject, so I will introduce some basic ideas. Okay, the motivation, then I will define the topological derivative. Then I will talk about some applications, in particular a benchmark example on structure topologization. And then the main part of my talk concerns inverse potential problem, which is joint work with Professor Prakash. Okay. So let's suppose that we want to minimize some quantity psi, which depends on geometric domain omega. Okay. And this geometric domain belongs to a set of admissible domains. So we want to change the shape and the topology of this domain in order to minimize this quantity. Okay, that's the motivation of the problem we are dealing with. So a quite general approach to deal with this kind of problem is based on the topological derivative. The idea is somehow simple. We have the original domain denoted by omega, and then somewhere in this domain denoted by the point x hat, which is an arbitrary point of the domain, we introduce some perturbation, like a hole, for instance. This hole, this perturbation, or the singular perturbation is denoted by small omega, and depends on the small parameter epsilon. And then we are looking for an expansion of this form where the shape function of the quantity we are interested defining the perturbed domain that depends on the small parameter epsilon and on the center of the perturbation. We will approximate by the shape function associated to the perturbed domain plus a first order correction of this form where we separate the dependence with the small parameter epsilon and the point, and plus remaining. Here, the notation is the following: omega epsilon of x hat is omega minus the small hole, small omega epsilon x hat, the closure, and f epsilon is a function that goes to 0 when epsilon goes to 0. And then, after rearrange the expansion, we can divide by epsilon and then pass the limit. So this limit is defined as the topological derivative. Note that this topological derivative depends only on the point x hat. So it doesn't depend on epsilon. So it's given by quantities defined in the original domain. Okay, it's like any derivative. However, the difficulty here is that omega epsilon and omega have not the same topology. So in order to compute this limit, or in order to evaluate this limit, we need some tools from asymptotic analysis. Okay, this is the main idea. So once we know this quantity, this first order correction, then suppose that we want to minimize this shape function, then we can use this first order correction as a steepest descent in an optimization process, for example, in order to minimize the shape function. So it has many applications for obvious reason in topology optimization, inverse problems, multiscale material design, image processing, fractal mechanics, and so on. Okay. For example, here I am show you some application in fluid dynamics. Here, for example, is the optimal channel that where we have input inlet flux here and two outlets here, and then this is the best, in principle, the best channel that divides the flux in this way. Here is an example on inverse gravity problem, where these small balls are hidden objects inside the Earth that we reconstruct them through some measurement of the potential on the surface of the Earth. Okay, and here is an example of design of metamaterials. This is a material with a negative Poisson ratio. It means that if we stretch in one direction, this material expands in the other direction instead of contracting. Okay. And here on the bottom, we have an example of a design of a structure subject to self-weight loading. Okay, and here in the middle, the design of Nanophotonic Designs. This is a non-antenna. Note that the scale is quite small. We have 2 micrometers here. Okay, and this is light. Okay, so the idea here is to maximize the power of this antenna in this region. Okay, so all these application we use the topological derivative. So in order to fix the idea, let me show a benchmark example on structure optimization. This is a quite intuitive application of this object. So here, imagine that we have elastic body, three-dimensional elastic body clamped here, subject to some traction on the boundary, and we want to study the behavior of the total potential energy of this structure with respect to nucleation of small holes, okay, inside the domain. So the shape function here is defined as the total potential energy, where U is solution to this elasticity system, where sigma of U is the Cauchy stress tensor, C is the elasticity tensor defined through the parameters E, which is the Young modulus, and E, the Poisson ratio. In this way, it's a fourth order tensor. And gradient of US is the symmetric part of the gradient, which is actually the linearized green tensor. Okay? U bar is some displacement prescribed on gamma D, on the boundary gamma D, and Q bar is some traction defined on gamma N. So here in the picture, we have gamma N here with some traction, and somewhere the structure is prescribed. For example, it's clamped, where U bar is 0, for example. Okay. So the idea is to introduce a small hole inside the domain. Here, the hole is actually a small cavity inside the domain with center at x hat and radius epsilon. Okay, So it's like a cheese. We have a small cave inside the domain. So we understand that this perturbation is a void, so it induces a Neumann boundary condition on the cavity. Okay. So if we compute the expansion of the energy with respect to epsilon, we get this expression where we can approximate the shape function defined in the perturbed domain by the shape function defined in the unperturbed domain plus this first order correction where we have, after using tools from asymptotic analysis, we can separate the dependence with respect to the small parameter epsilon, which is the radius of the perturbation here, and some quantity which does depend on epsilon, which is defined through quantity evaluate on the original domain omega. Okay, so remember that U here, U is solution to the original problem defined in omega. Okay, so here it appears this object is called the polarization tensor that comes out from the asymptotic analysis of the solution, which is given by a fourth order tensor that depends on the material properties of the background. Okay, this polarization tensor plays a key role on the analysis. So let me show an application of this formula. Suppose that we want to, since this is represents the total potential energy, so we want to minimize the compliance. So the compliance is minus the total potential energy with a volume constraint, which is introduced here as through a penalty parameter beta. So the topological derivative of the compliance we know is given by this formula, which comes out from the asymptotic analysis of the total potential energy. And then the topological derivative of the volume is trivial. It's given by this quantity. And then here we have the structure that we want to find the optimal topology according to this measure. Okay, so we have a cube simply supported on the top, on the bottom with a load on the top. Okay, so the idea here, we solve this problem using, for example, finite element method. We compute U, we compute the strain, and then we compute the stress. We replacing this formula, and then this will give us a scalar field representing the sensitivity of this quantity when we introduce some small hole on the domain, inside the domain. So since we want to minimize this, we have to introduce holes where this quantity is more negative, for example. So if we do it in an iterative process, we get this kind of solution. So the idea here, we introduce a small hole, for example, according to the topological derivative field. Okay, and then we compute again the solution of the state equation and compute again the topological derivative and use this new information to introduce new holes and so on, and we get a kind of descent direction to minimize the problem. And then we have this benchmark structure, let's say. Okay. So now let me present the main part of my talk, which is, as I told, it concerns applications of the topological derivative method to solve an inverse potential problem. This is a joint work with Professor Prakash and Fernandez, which is a former student from my institute. So the problem is the following. Suppose that we have a domain omega with some anomalies inside. Okay. And then, but we don't know where these anomalies are. We want to reconstruct them from some measurement taken on this small domain omega O. Okay. So the direct problem is governed by this PDE, where zeta is solution to this boundary value problem with some boundary excitation on given by J. Okay, we suppose that this anomaly has compact support on small omega star. Okay, so this inverse problems is opposite. There is a lack of uniqueness if the coefficient k and the shape of omega star are unknown. So we assume that k is given, and then we want to find the support of the potential omega star. So the paradigm here is the following. We know what we are looking for, but we do not know where they are. Okay. So the uniqueness of this inverse problem seems to be an open problem. Okay. According to Isakov. So the idea here is to rewrite this problem as a topology optimization problem. So we want to minimize the misfit between over omega O between the measurement zeta solution to this problem, okay, and U with the solution to this auxiliary problem. It has the same boundary excitation, but with some k omega arbitrary. So of course, if omega coincides with omega star, we have that U is equal to zeta everywhere, and in particular over omega O, and then we get the minimum. So we want to minimize this quantity with respect to small omega, provide that we know the value of k. Okay. So in this case, we suppose that small omega is empty. So a small omega actually is our initial guess, let's say. We suppose that this is empty. And then we compare the solution U without any anomaly with zeta, which has been obtained from a problem with a small anomaly or a number of anomalies. So the idea here is to use the topological derivative method. So we start by introduce a number of small perturbations given by these small balls of center in xi hat and size epsilon I. Okay. So after perturbing the domain with a number of small anomalies in this way, we have a new functional associated to the perturbed problem, where U epsilon depends on the small parameters epsilon, 1 up to n, okay? Here's just a notation. We write this as a a vector, and this is as a small matrix, provided that xi is in R2. Okay? And then from these elements, we can get this expansion where the shape functional associated to the perturbed domain is approximated by the shape function associated to the unperturbed domain, plus a first order correction term. Note that here can be understood as the topological derivative, first order topological derivative, this quantity d, and alpha is the proportional to the measure of the perturbation. Okay, this is the volume of the area of the small ball, small anomaly. And then we have two more terms. This term, which is of second order with respect to alpha. So H can be interpreted as a Hessian matrix. And there's this intermediate term, which is in between alpha and alpha square, okay? And plus are remaining. So let me explain each term. So the entries of the vector d is given by this quantity, which is u at the point we are introducing the perturbation, times v. V is the adjoint state solution to this problem. Remember that u0 is solution to this problem, since we take small omega as empty set. So the problem free of any anomaly. And the adjoint state is a solution to this PDE. And then we have this quantity J, which appears here, okay, this matrix, which is given by this one. This quantity is completely defined by the direct and joint states. And then the Hessian matrix is given by this formula, where this is the diagonal of the Hessian matrix. This is the extra diagonal terms, which depends on the direct and joint state, and also depends of this QI and HI. Okay, and here J, HJ, HI, and so on. And QI and HI are solutions to this set of canonical PDs. Okay, canonical in the sense that they does depend on they don't depend on the anomalous. So remember our expansion we have found. Then, since we want to minimize this functional, then we can the idea is truncate the expansion and observe the behavior of this quantity here. So the idea, so if you want to minimize the shape function, then we want to minimize this quantity, which is the explicit part of the expansion. Okay, so here is the heuristic we are using. I mean, we are truncating the expansion and trying to build the reconstruction algorithm from the information we have at hand, which is this one. Note that this is a kind of quadratic form with respect to alpha. So we can minimize this quantity with respect to alpha to get this system of this linear. It's not this system. It's non-linear with respect to alpha. And then after solve this system, we come back to this expansion, and then we can find the locations of the anomalies by solving this simple optimization problem. So finally, the solution to the inverse problem is the pair of C star and alpha of Xc star, where alpha represents the size of the anomalies and psi represents the locations. Okay, this is the main idea. So let me show some numerics to fix the idea. Suppose that here we have the target to be reconstructed given by 3 anomalies. This gray region is where we are take measurement. Is the so-called omega O. So the idea is the following: we solve the problem, and then we take the solution restrict to this gray region, and from this information and using this algorithm, we will try to reconstruct these anomalies. Okay. So with no noise, we have the reconstruction here. Here's the target with no noise, and the reconstruction is quite exact. Not that this reconstruction is non-iterative, because once we solve this problem, we have the optimal size of the anomalies. Then after solve this one, we have the optimal location. That's all. So after solving this simple optimization problem, we get the anomalies here. Okay, which is somehow exact reconstruct, provide that the remainder here is small. And then we corrupt the target with some 20% of noise, and we get the reconstruction, quite good reconstruction. With 40% of noise, we still get a good reconstruction. Okay, there is small error in the location of this anomaly, I guess. And finally, with 8% of noise, the solution starts to degrade. So not that the target is corrupt with a very aggressive level of noise, and even though we can get a good reconstruction. Why? Because the reconstruction algorithm based on this high-order topological derivative method is non-iterative. So because of that, it's quite robust with respect to noise data. So let me conclude my talk. I would like to say that this approach allows for reconstructing multiple anomalies simultaneously. It's independent of an initial guess. For our initial guess is the empty set in this case, so it's completely independent of the initial guess. And since the reconstruction algorithm is non-iterative, so it is very robust with respect to noise data, as shown in this picture, that we have a very degraded target, and the reconstruction is still quite good. So thank you very much, and I am available for discussion.
Okay, thank you very much, Professor Andre. It's familiar to me, but every time I see, I find it interesting. I have a couple of questions that I will ask later, but let's talk, ask the audience if they have. Yeah, si alguien tiene pregunta, duda, por favor, puede preguntar. Rajesh, please go ahead.
Hi, Andre, long time. Glad to see you, and it was a very nice talk. So I have a few questions. So although I like, I'm a bit familiar with shape derivative, not so much with topological derivative. And my question, there are several questions. Some are maybe trivial and maybe some you can are probably more pointed. So in the example, there were like you could only locate the anomaly given the shape, or you can also with the same thing you can reconstruct the shape.
Oh, hi, Rajesh. Nice to meet you.
Yeah, I'm happy. Sorry, I'm not with my camera. Yeah.
So let me try to answer your question. Actually, this is a self-regularized approach that we are somehow approximating the shape of the unknown anomaly by balls. Okay.
Mm-hmm.
So what we find is the location of the barycenter of the anomaly, and about that replace the anomaly of any shape. Okay.
Mm-hmm.
What we observe, there is no proof, but what we observe is that, for example, if we have some funny shape like L-shaped anomaly or something like that, we can approximate it by a number of balls.
Yes.
This way, but this is purely numerical speculation. We have no proof. But in principle, it works quite well. If we have some anomaly which is not a circle, a ball, then we can approximate by a number of balls.
Yeah, it's intuitive. It would be interesting to maybe investigate more theoretically what could happen. So I would be interested, for example.
Yes, and even if you just deflect from the circular to something else, it is a disaster. It means we have so much issues with that theoretically, of course.
Yeah.
One thing also to observe here that whatever result mathematically he showed, we found that was for the without noise, no noise. It was completely deterministic. But the numerically, what result he showed, it has with the noises, and it works. The numerics.
Yeah.
That's very
I
interesting.
have another question. So it's on the page 19, the theorem, the result for the sensitivity analysis. So, so you have a expansion for the topological derivative, and I understand it's a higher order derivative because you have the higher order tensors alpha, tensor log alpha, and so there are two questions. So I was a bit curious to know why the tensors depend on the logarithm of the sizes of the balls, the volumes, and the second one, is there some general structure theorem you can try to prove? Meaning, is it known? So,
This theorem is we actually prove it.
yes.
I mean, the proof is the following. We get these three terms explicitly and a remainder that which is a higher order on epsilon. That's all. Why it's given by actually this intermediate term depend on logarithm of alpha. It was a surprise for us, but it comes out from the ansatz. We have to solve by hand some problem, and then these solutions are given by Bessel functions. And this comes out from the Bessel functions, which are basis of the solution to the auxiliary problem that we solve by hand. Basically, it comes out from the analysis. I'm not sure.
I think if I remember correctly, when we were doing it, If we do the same problem for dimension 3 or more, this logarithm term will not appear because it was coming from the fundamental solution of the Laplacian.
Yeah.
So Rajesh, if we do the same problem for R3 or more, that logarithm will get vanished. So you will get the order epsilon square epsilon cube, not epsilon square then epsilon log epsilon.
Yeah.
In 3D, it's epsilon 3, epsilon 5, and epsilon 6.
Something like yes.
But it comes out from as Professor Prakash told, it comes out from the fundamental solution of the operator. So depends on the operator. For example, if there is no this zero order term on the equation, for example, if the unknown is on the right hand side, for example, we have epsilon square and epsilon 4. There is no intermediate term, for example. It depends on the operator for sure. From the asymptotic behavior of the solution.
So that's all my question for. Thank you very much. Yes.
Thank you.
¿Alguien más tiene duda, pregunta, comentario, consulta?
Yo tengo una pregunta. I have a question. Thank you very much for your talk. And I want to ask why the perturbation is a ball and not another structure?
This is a good question. Actually, a priori choice for us. We choose balls because we can get this expansion explicitly. That's the only motivation. For example, if you remember the expansion, it's explicitly given in terms of the adjoint state, the solution to the direct adjoint state, and the solution to some auxiliary problems. That depends on the point, and that's all. If we take something which is not a ball, it's not a circle, it's like, for example, a square or something like that, we cannot get this quantity explicitly, but actually it doesn't matter because we can solve this problem numerically. But if it's circles, we can solve by hand.
Yes.
Yeah.
Okay. Thank you.
Actually, for any shape, it appears the polarization tensor, which depends on the shape of the perturbation. And this polarization tensor, it's somehow encapsulated there. We compute it by hand, but if it's not the case, we have to, for example, compute polarization tensor numerically. And that's all. So the problem becomes heavy and more involved to code. So because of that, we choose cycles.
Okay, thank you.
Okay. You're welcome.
¿Más preguntas, dudas, comentarios, consultas? Si no, agradecemos, Professor Andre Novotny. Thank you very much, Professor, for the talk. It was really interesting. My question comes now. My question is about as we discussed, the uniqueness of the topological derivative is not guaranteed, right? As we also discussed with the Jan sometime, if you remember, in the canteen. So if it is not defining this derivative directly connected from the Taylor's expansion makes sense, not like the fraction which we do for the general derivative in analysis.
Mm-hmm.
Yeah.
Yeah.
So we cannot define the topological derivative from the like analysis. So we are actually defining it analogously to the Taylor's expansion, and the cost which we are paying is loss of uniqueness. Done. So my question is, before it existed, no, the notion of topological derivatives, when Ian and the other people defined it. So it became significant when it was numerically applicable, right? Make sense?
Yeah.
Yeah. So your algorithm, which was the second order algorithm, became significant crucially once it reduced the cost and started calculating the anomalies, for example, reconstructing the anomalies.
Sorry, I didn't get your point.
This theory became significant once the applications came from the engineers, right? Okay. No, I'm just confirming it. I had this thing in doubt, right? Because theoretically it's not so advanced. There are lots of huge amount of work to be done in this area, but numerically as we saw in your results that it's creating good results. So it became significant or maybe important for the researchers' point of view when it became applicable, right?
Yeah.
Okay. So if the problem is not, for example, the fractional derivative, which with the nonlinearity, so for example, with something weird, PD nonlinearity and something, then what will happen?
Yeah, this is a good question. For non-linear problems, it depends. For linear problems, it's more or less under control. But for non-linear, it depends strongly on which kind of non-linearity. For example, it's very easy to construct a counterexample. For example, the P-Laplacian does not admit topological perturbations.
Boom.
For example, for the P-Laplacian equation, P greater than 2, we cannot make holes. Okay, the U epsilon doesn't convert to U when epsilon goes to 0 in any. So it depends, of course. For example, for Navier-Stokes equations, we have topological derivative. For example, there are some class of nonlinear problems that allows topological perturbations like that. Of course, we can find many counterexamples that we cannot. It's forbidden.
Next, okay.
So it depends strongly on the problem. Actually, this is I think the main issue on asymptotic analysis that it's not axiomatic. Strongly on the problem we are dealing with. The construction of the ansatz and so on, there's no any recipe. We have to know some properties of the solution a priori to try to find some ansatz that fits our theory.
True. In fact, it had nothing to do with PDE. It means maybe the optimization problem is the point to start. Yeah. Rajesh wants to say something.
It depends on the shape function for sure.
Yeah. Okay, Rajesh wants to say something.
I have a comment which has nothing or very little to do with the actual talk, but nowadays one hears so many talks now on deep learning and those kind of things. So I mean, so for these kind of problems, this detecting anomalies, etc. And do you think there are new directions other than topological and classical methods which we use, which we like, to train and find the shapes in some sense? Like, are you aware of anything in that direction?
No, I'm not. Let's say that I'm not aware because it's a field that I never studied. But of course, there are many even if we don't talk about optimization, but the modeling itself, there are many meta models that give very good results for complicated problems like petroleum industry and so on, and they do not solve any PD. This is you see, it's another, how can I say, another branch of research that can have an impact, a strong impact in the industry for sure. But it will reflect on the optimization also. Also, we have some meta models to deal with big problems from industry. We can also thinking on optimization. Why not? But I am ignorant on this, so I just heard about. But there will be in competition, I think, in the near future. But I'm not sure because, for example, this meta heuristic, like a genetic algorithm, it was so promising some time ago, and now I'm not sure if it's a good approach if we know nothing about the problem. I mean, if the problem is no differentiable, or if you know nothing, then you can try some meta heuristic to solve your problem because you have no choice. But if you can solve a problem with some gradient method, is much better because you have a strong theory behind. For example, they talk about, for example, global minimum, but they do not guarantee even local minimum. But in gradient-based method, at least we are sure that we are landing in a local minimum, for example, at least. So you see, it depends. But sometimes it's impossible. There are many problems that you cannot differentiate, for example. Then we have to use some meta heuristic approach. No way. But I think this is a concern which comes out from the industry because they have big and really difficult problems to solve, like in petroleum industry. For example, they know nothing about. They do not know the permeability map of the basin, for example. And then they have to solve the problem. Or in forecast. Forecast is the same. It's so complicated the problem that the deterministic method will fail miserably.
I agree with you because once I was giving a talk in IIT Delhi, and there are many audience people were from the engineering, and they were really worried about this, for example, the petroleum.
Yeah.
It means, and but they were insisting on the non-linearity again and again and again.
Yeah. Actually, it's a different concern. I mean, for this history of topological derivative is quite limited for some elliptic problems and maybe some non-linear problems, but it's quite restrictive. But it's very nice subject to do research. It's more or less under control, and then we can find some nice application. But if we want to solve some big problem of industry, I think topological derivative is a bad idea. But who knows in the future?
We have one more question or comment from AF Palma. Please ask your question. I think he does not have a mic. He wrote, "Nice presentation. I have a question. What are the main numerical techniques used to focus solutions to problems in this form of optimization?"
In what?
I have a what are the main numerical techniques used to focus solutions to problems in this form of optimization?
Actually, how to answer this question? In principle, the topological derivative it's independent on the numerical method. It's somehow semi-analytical approach to optimize or to solve some inverse problems. And for example, this quantity we have to compute, which comes out from the expansion, we can compute using any numerical method. I am very familiar with finite element method, so I use finite element by a personal choice. But you can use any approach, even if you are able to compute everything by hand, okay, much better. But you can use boundary element to solve the PDEs. We have some auxiliary PDEs to solve. So these PDEs you can solve using any method designed to compute PDEs, the solution to PDEs, like boundary element, finite element, finite difference. It doesn't matter in principle. Of course, there is a deep discussion after. For example, this is a very important discussion. If we first discretize and then optimize, or if we optimize and then discretize, the result normally is not the same. So there is some some gap here to fill for sure. This is a deep question also. For example, using topological derivative, we first optimize and then discretize. I mean, we have the sensitivities, which is somehow semi-analytical, and then in order to evaluate these sensitivities, we have to discretize and so on. And then a good question that arises is if it's equivalent, or in which sense. I mean, if the discretized version of the topological derivative converges in which sense to the continuous one, for example. This is a somehow open question. I have no answer.
Okay. ¿Alguien más quiere decir algo? Yes, Rajesh, you want to say something?
No, just I don't know what's the plan. So
the plan is to go and take the biscuit in your home and take coffee.
no, so
That's good.
happy to see Andre again, and hope you can come and visit us when all this is over, and it'll be a joy.
It was my plan actually. It was my plan, but eventually this corona destroyed everything.
Yeah.
Let's see next year.
Yeah, sure.
Because here in Brazil, we are late with this vaccination. It's messy.
Here also, I think Chile one doesn't know, but that we have less population, and maybe that's useful. So
We would like to thank the audience for the nice discussion, and I try to be, how can I say, quickly just to introduce the subject, and in my web page you can find if some prototypes code in MATLAB if you want to download and try and see how it works. But in any case, thank you very much, Javi, for the invitation.
No, it was completely my pleasure, because I am seeing you first time talking. Otherwise, generally we have discussions. Ok, entonces agradecemos al profesor André, y si alguien quiere, si nadie tiene preguntas, duda, comentario, cerramos el coloquio, ¿ya?
Okay.
Have a good day, André. See you later.
See
Bye.
you. Bye-bye.
Okay, muchas
See
gracias.
you. Bye.
Muchas gracias. Chao, chao.
Ciao.
Ciao.